Bismillahirrahmanirrahim. Assalamualaikum and very good morning. And for today, we will move into the next chapter, chapter number 8. The title is Flow in Closed Conduit, or in some books, the title is Flow in a Pipe. Okay, what is closed conduit? It is a closed passage, such as a pipe, for example. Okay, in this particular chapter, we are going to cover 4 main items, which start with the Reynolds number and the entrance region. Next is lamina and turbulent flow in pipes, minor losses, and last is the flow rate and velocity measurement. Okay, for the Reynolds number and entrance region, okay, as you know, the transition from the laminar to turbulent flow depend on the geometry, surface roughness, flow velocity, surface temperature, type of fluid, and among other things. Okay. After exhaustive experiment in 1880s, Osborne Reynolds discovered that the flow regime depends mainly to the ratio of initial force to viscous force in the fluid. Okay, this ratio is called the Reynolds number, and it is expressed for internal flow in a circular pipe as so. So Reynolds number, okay, Reynolds number is equal to the ratio of initial forces to the viscous forces. And it is also equal to the rho, which is the density, multiplied by the average velocity, V average, then multiplied by the D. D is actually the characteristic length. Okay, this D here is the characteristic length. Characteristic length. Okay, D. Okay, if you are interested on something which is a region with not it is not a pipe, for example. Okay, if it is a pipe, we normally refer to the diameter of that particular pipe. Okay, if it is external flow, then D we normally replace by the L, which refer to the for example, if you are looking into the wing, L could be the chord length of that particular wing. If you are talking about the wing, this could be the shape of the wing itself. So this length is the chord length, and C, or the length here, would be replaced here. So become rho V C over mu. Okay, instead of D, if you are talking about the wing of the aircraft. Okay, moving on. As I mentioned just now, that Reynolds number is equal to the initial forces, the ratio between the initial forces to the viscous forces. And if you do the math, you can rearrange that equation into this. Okay. At large Reynolds number, the initial forces, which are proportional to the fluid density and the square of the fluid velocity, are large relative to the viscous forces, and thus the viscous forces cannot prevent the random and rapid fluctuation of the fluid. At small or moderate Reynolds number, however, the viscous forces are large enough to suppress this fluctuation and keep fluid in line or become smooth. Thus, the flow is turbulent in the first case, okay, and laminar in the second part of this. The Reynolds number at which the flow becomes turbulent is called the critical Reynolds number, or denoted as Re subscript Cr. Cr stands for critical. The value of the critical Reynolds number is different for different geometries and different flow condition. It is different. Remember this. For internal flow in circular pipe, it is the general accepted value. Okay, the general accepted value of the critical Reynolds number is 2,300. Okay, roughly this is the number that being accepted by the fluid community, I would say. Okay, but this particular number, again, it is different for different geometries and flow condition. It might change slightly. Okay. For if you refer to this different type of cross section of pipe or passage, you can see that on top we have a circular tube. Okay, we have a circular tube, and then we have a square duct, and we have a rectangle duct. It is to give you some ideas, okay, how to actually determine the value of this particular D. Okay, or in this case, yeah, DH, the same thing lah. BH, right? So this is the process. So for circular tube, it is very simple, where you just take the diameter of that particular tube. However, for a square duct, you might need to just stick to one of the edge, okay? And for rectangular duct, you may need to use this approach, okay? Okay, under most practical condition, the flow in a circular pipe is, you have here laminar flow, where the Reynolds number is lower than the 2,300, and it is said to be in the transitional flow, where the Reynolds number is in between of 2,300 to 4,000. Okay, above 4,000, we can consider it is a turbulent flow. Okay, note that in transitional flow, the flow switches between laminar and turbulent randomly. It should be kept in mind that the flow can be maintained at much higher Reynolds number in very smooth pipe by avoiding flow disturbance and pipe vibration. Okay, so in such carefully controlled experiment, laminar flow has been maintained at Reynolds number up to 100,000. Okay, so although this is our general accepted values, okay, this is our general accepted values for the circular pipe. However, under certain condition, the Reynolds number can be maintained in a laminar state of flow up to 100,000 Reynolds number. Okay, so if you can see from this image here, you can see that what happened is this is a snapshot at the test section of I believe this could be the water tunnel, right? Could be the water tunnel. Okay, what happened is inside this water tunnel, it is filled up with the water, and that particular water is moving from the left to the right at the speed of v. Okay, this is the average velocity of that particular flow. And here there is a tube. that is in this particular tube, we inject some amount of dye. Okay, let's say it is a black color or red color, so that we can see the trajectory, or we can trace the dye as it moves together with the fluid, with the surrounding fluid, which is moving from the left to the right, right? So from there, we can see what's going on to this particular dye, whether it will maintain smoothly or it will become chaos, or, you know, become turbulence. Okay, become a random movement. Okay, the flow is said to be laminar, okay, characterized by smooth streamlines and highly ordered motion. And turbulent is the second case, where it is categorized by velocity fluctuation and highly disordered motion. And in between them, the transition from the laminar to turbulent flow does not occur suddenly. Rather, it occurs over some region in which the flow fluctuates between laminar and turbulent before become fully turbulent. Most flow encountered in practice are turbulent. Laminar flow is encountered when highly viscous fluid, such as oil, flow in small pipes or narrow passage, or narrow uh, uh, cross-section of area. Okay. Okay. The existence of this laminar, transitional, and turbulent flow regime can be verified by injecting some dye streak into the flow in a glass pipe, as what have been shown by British engineer Osborne Reynolds, okay, somewhere in Manchester last time, between 1842 to 1912. Okay, it is observed that the dye streaks forms a straight and smooth line at low velocities when the flow is laminar, and has bursts of fluctuation in the transitional regime, and zigzag rapidly and randomly when the flow becomes fully turbulent. This zigzag and dispersion of the dye are indicative of the fluctuation in the main flow and the rapid mixing of fluid particles from adjacent layers. The intense mixing of the fluid in turbulent flow as a result of rapid fluctuation enhance momentum transfer between fluid particles, which increase the friction force on the surface and thus the required pumping power. The friction factor reaches a maximum when the flow becomes fully turbulent. Okay, and as you can see on the left here, okay, we have two conditions, where on the top we have a laminar flow and the dye trace is in a straight line. Okay, and then down here we have a turbulent flow, and if you can see, the dye trace here is become chaotic. Okay, is random. Okay, speaking of the flow inside a pipe, okay, imagine that at this point, this is our entrance of the pipe. Okay, the development of the velocity boundary layer in here, what's shown is the development of the velocity boundary layer in a pipe. The developed average velocity profile is parabolic in laminar flow, as shown. Okay, it is rather parabolic. but somewhat flatter or fuller in turbulent flow. Okay. As you can see, in a fully developed flow, this is the profile that you will get. Okay, it's kind of parabolic. Okay, consider a fluid entering a circular pipe at a uniform velocity. Because of the no-slip condition, the fluid particles in the layer in contact with the surface of the pipe come to a complete stop. Okay, this layer also causes the fluid particles in the adjacent layers to slow down gradually as a result of friction. To make up this velocity reduction, the velocity of the fluid at the midsection of the pipe has to increase to keep the mass flow rate through the pipe constant. As a result, a velocity gradient develops along the pipe. The region of the flow in which the effect of the viscous shearing force caused by fluid viscosity are felt is called the velocity boundary layer, or just the boundary layer. The hypothetical boundary surface divide the flow in a pipe into two regions. The boundary layer regions, in which the viscous effect and the velocity changes are significant, and irrotational, in which the frictional effects are negligible and the velocity remains essential constant in the radial direction. The thickness of this boundary layer increases in the flow direction until the boundary layer reaches the pipe center and thus fills the entire pipe. The region from the pipe inlet to the point at which the boundary layer merges at the center line is called the hydrodynamic entrance region, and the length of this region is called the hydrodynamic entry length, LH. Okay. Flow in the entrance regions is called hydrodynamically developed flow, since this is the region where the velocity profile developed. The region beyond the entrance regions, in which the velocity profile is fully developed and remain unchanged, is called the hydrodynamically fully developed region. The flow is said to be fully developed when the normalized temperature profile remains unchanged as well. Okay, in the fully developed flow region of a pipe, this is what is shown. The velocity does not change downstream, and thus the wall shear stress remains constant as well. Okay, we want to speak about the entry length. What does it mean? Okay, the entry length, or the hydrodynamic entry length, is usually taken to be the distance from the pipe entrance to where the wall shear stress reaches within about 2% of the fully developed value. In laminar flow, the hydrodynamic entry length is given approximately as this. Okay, you can refer to the Case and Crawford 1983 and Shah and Bhatti 1987, the references for that. Okay, for the laminar entry length, it is approximately 0.05 Reynolds number times the diameter of that particular pipe. Okay. For example, for Reynolds number equal to 20, the hydrodynamic length is about the size of the diameter, but increase linearly with velocity. In the limiting laminar case of Reynolds number 2300, the hydrodynamic entry length is 115 of its diameter. Okay. So in turbulent flow, the intense mixing during random fluctuation usually overshadows the effect of molecular diffusion. The hydrodynamic entry length for turbulent flow can be approximate as shown here. Okay, just now there is approximation for the laminar flow, and now we are talking about the turbulent flow. Okay, then the entry length is much shorter in turbulent flow as expected, and its dependence on the Reynolds number is weaker. Okay, the Reynolds number is weaker. In many pipe flows of practical engineering interest, the entrance effect become insignificant beyond a pipe length of 10 times of its diameter, and the hydrodynamic entry length can be approximate as so. Okay, it's about 10 times of its diameter. Okay, this is the variation of wall shear stress in the flow direction for flow in a pipe from the entrance region into the fully developed region. As you can see, okay, from here to this point, it is, we call it as entrance region, and from this point onwards, it's called fully developed region. Okay, what is happening from this point onwards, as you can see that this particular line become constant, right? It's not changing with this x-axis, or it doesn't change at all, right? As it move to the right. Okay, that is what we call fully developed region. Whereas in the entrance region, there are decrease, or there are changes in the wall shear stress, as you can see from this particular plot. And down here is the cross section of that particular pipe. Okay. In fully developed laminar flow, each fluid particle moves at a constant axial velocity along a streamline, and the velocity profile, you can denote it as UR, remain unchanged in the flow direction. There is no motion in the radial direction, and thus the velocity component in the direction normal to the flow is everywhere 0. There is no acceleration since the flow is steady and fully developed. Okay, the relation for pressure loss is one of the most general relations in fluid mechanics, and it is valid for laminar and turbulent flow, circular or non-circular pipes, and pipes with smooth or rough surface. And we can use F as our friction factor, or in this case, we call it Darcy friction factor, which represent how smooth or how rough is that surface is in relation to this pressure loss or head loss. Okay. And for the pressure losses, delta PL is equal to the Darcy friction factor multiplied by the length of the pipe times the density of that fluid, the speed of that, the average velocity of that fluid divided by the diameter of the pipe. The pumping power requirement for a laminar flow piping system can be reduced by a factor of 16 by doubling the pipe diameter, as I've been shown here. Okay, where on the top here we have the pumping power, W dot pump is equal to 16 horsepower. H stand for horse, P stand power, horsepower. And can see the diameter is D, 1D, whereas down here, you increase the diameter by double the diameter of the pipe. And then you can see the power requirement is only 1 horsepower. Okay. This is the power pumping power requirement for laminar flow piping system, which can be reduced by a factor of 16 by doubling the pipe diameter. Okay, now this is some of the friction factor which you can see for a circular, for a rectangular, for an ellipse, and for isosceles triangle, or for a triangle. Okay, so there are different values of the friction factor. And again, if we want to see the roughness of that particular material, then you can refer to this particular table. This particular table I took from the book of Chenga Chembala. Okay, so for example, like a glass, glass is very smooth, so the roughness is 0. For concrete, it is 0.003, okay, up to 0.3. For if you measure it in feet, if you're measuring it in millimeter, then it is your values. Okay, make sure that what is your measurement unit is, okay? Whether you refer to the SI unit or the British unit or American unit, standard unit. Okay. Okay, we have an example. I will go through this particular example in the other videos. And for the turbulent flow, it is categorized by random and rapid fluctuation of swirling regions of fluid called eddies. Okay, when there are a lot of fluctuation, and actually we can see the eddies, okay, throughout the flow. This fluctuation provide an additional mechanism for momentum and energy transfer. Okay, if let's say you want to enhance the energy transfer within a certain pipe flow, then you may require to produce flow which is highly turbulent. Okay, so that the momentum and energy transfer can be more effective. Okay, in laminar flow, fluid particles flow in orderly manner along path line, and momentum and energy are transferred across streamline by molecular diffusion. In turbulent flow, the swirling eddies transport mass, momentum, and energy to other regions of flow much more rapidly than molecular diffusion. And it is greatly enhanced mass, momentum, and heat transfer. As a result, turbulent flow is associated with much higher values of friction, heat transfer, and mass transfer coefficient. Okay, so here you can see there is a before turbulence, okay, and this one is after turbulence. What is the difference? Okay, on this part, as you can see on the top here, all is with number 2, and next is number 5, number 7, and last row is number 12. And then on this side, we have a mix, right? Mix of the numbers. Okay, the intense mixing in turbulent flow brings fluid particles at different momentums into close contact and thus enhance momentum transfer. Fluctuation of the velocity component U, okay, this part here, this axis, with time at a specified location in turbulent flow. If you are measuring it over time, and this is what you can see. There are fluctuation of the velocity. And therefore, you can see when this is happening, it's most likely that the flow is turbulence and it is a mixing happen. Okay, the velocity gradient at the wall and thus the wall shear stress are much larger for turbulence flow than they are for the laminar flow. Even though the turbulent boundary layer is thicker than the laminar one for the same value of free stream velocity. Okay, as you can see here, imagine that this could be the wall. Okay, similarly down here, where you can see for turbulent flow, the shape is more flattened, right? Because on this part here, there is a lot of shear stress. However, on this part, no, the shear stress is not present. It is if you look into the whole pipe system, whereas here we just look at half of the pipe cross section. Okay, the velocity profile in fully developed pipe flow is parabolic. Okay, in laminar flow, here is parabolic as you can see, right? But much fuller in turbulent flow. It is more like this, fuller or flatter in this turbulent flow. Okay. Okay, now we want to talk about the Moody chart. Okay, the friction factor in fully developed turbulent pipe flow depends on the Reynolds number and the relative roughness, which is the ratio of the mean height of roughness of the pipe to the pipe diameter. Okay, sigma is the height of the roughness, and d is the pipe diameter. The functional form of this dependence cannot be obtained from a theoretical analysis, and all available results are obtained from painstaking experiment using artificially roughened surface. Okay, so to obtain these values, this ratio, you cannot do it through theoretical analysis, but you have to do the meticulous experiment, you know, to actually get what are these values. Okay, most experiments were conducted by parental students named Nicholas in 1933, followed by the works of others, of course. Okay, the friction factor was calculated from the measurement of the flow rate and the pressure drop, and this is the relation that you can see between this friction factor with the Reynolds number. Okay, what you can see here, as the Reynolds number is increasing, the friction is reducing, right? Generally, it's reducing. However, if you see it closely, okay, for example, like these particular lines here, okay, From this point onwards, the line is flattened. Okay. Seems that from this point, let's say at this particular point, at 3 times 10 to the power of 5, okay, Reynolds number, the changes in the friction factor is no longer exists, no more changes. So you can say that at this point, the Reynolds number are not affected by, the friction factor is no longer affected by the Reynolds number. Okay. Okay, a simplified version of the previous Moody chart is shown here. Okay, at very large Reynolds number, the friction factor curve on the Moody chart are nearly horizontal, right? It's become constant, and thus the friction factor are independent of the Reynolds number. Okay, up to certain point, like this one, from here towards as you increase the Reynolds number, the value of this friction factor is remain the same, right? Like for this one as well. Okay, this line, this, and this one is actually from a different material or surfaces. Okay. Okay, now we want to talk about the minor losses. Just now, we talked about the heat loss. What being discussed just now is related to heat loss. Okay. Now we move into the minor losses. The fluid in a typical piping system passes through various fitting, valve, bends, elbows, T's, okay, T's, inlets, exits, enlargement, and contraction in addition to the pipe. These components interrupt the smooth flow of the fluid and cause additional losses because of the flow separation and mixing that they induce. In a typical system with long pipes, these losses are minor compared to the total heat loss in pipes and are called minor losses. Although it is generally true in some cases, the minor losses may be greater than the major losses. This is the case, for example, in systems with several turns valve within a short distance of a piping system. The heat loss introduced by a complete open valve, for example, may be negligible, but a partially closed valve may cause the largest heat loss in the system, as evidenced by the drop in the flow rate. Flow through valve and fitting is very complex, and a theoretical analysis is generally not plausible. Therefore, minor losses are determined experimentally, usually by the manufacturers of the component. Okay. Imagine that this is sort of a valve from your piping system. As you turn this pipe, it will go up and down, right? Due to the thread of this long threaded surface here. Okay, it will close this piping system. Okay, for a constant diameter section of a pipe with a minor loss component, the loss coefficient of the component is determined by measuring the additional pressure loss it causes and dividing it by the dynamic pressure in the pipe. Minor losses are generally expressed in terms of the loss coefficient, K subscript L, also called the resistance coefficient, defined as K subscript L is equal to the H subscript L divided by the V square over 2G, where HL is the additional irreversible head loss in the pipe system causes by insertion of the component and is defined as, okay, and delta PL is obtained from here. And what is this part is, it is from here. And this part here is from here, okay? So for this part here, you put the pipe section with valve. This is your valve. And down here, you take the differences between this and 0.1 and 0.2 without the valve, okay? Then you take the differences. Then this is your delta PL, or okay. For the minor losses, as we have discussed, or I have shown earlier, like a T section, it is more like a T section, right? And it is the elbow where the flow is coming in through this. It is a very sharp turn. So as you can see, if, okay, try to compare between this and this one and this one down here. Okay, what happens is, if you have this curvature, it actually will help the flow from this point to this point. Whereas if you have a very sharp turns like this, what happens is the flow will be disturbed. Okay, the flow will have will create a sort of a region here. Okay, and this particular region will eventually create some sort of losses. Okay, some sort of pressure loss. And therefore, if you compare the value of this K, L, you can see that it is just 0.3 and this one is 1.1, which is much higher compared to this. That is due to the high amount of losses on this part. Okay. Similarly, if you compare with this part here and this part, this is very sharp, right? And this one is more curved. It has some curve. So the value for curve because is lower than this one, because here it allow the flow to enter this region much smoother, okay, without creating this recirculating flow, okay, like this one. This is some example of loss coefficient, or KL, of various pipe component for turbulent flow. Okay, you may refer to this if you would like to solve a problem which have which you need to deal with this sort of minor losses. Okay. This is the relation of this loss coefficient with this diameter of that particular pipe. Okay, what's D is actually the small pipe here, diameter, and the capital D is the this large pipe where the fluid is entering from the larger pipe to the smaller pipe, and you take uh, the square of both, and take the differences, the ratio of it, right? Okay, and it is, if you have this sort of geometry, you may refer to this and this one. Okay, whether it is from a smaller to the bigger size, or from the bigger size of pipe to the smaller size of pipe. So you can refer to this two. Or we can call it, one is expansion, the other one is a contraction. Okay, all the kinetic energy of the flow is lost. Okay, basically it turns into thermal energy through friction as the jet decelerates and mix with ambient fluid downstream of a submerged outlet. And what you can do, or what you can experiment on your own at home or at the college, while yeah, at your free time, but don't waste water. Basically, if you want to fill up a bucket of if, with the water, then you may try to use, or you may try to uh, get a phone with you, and you may take make it as your stopwatch to measure how long does it take for the water to fill up this particular bucket, for example. Okay, and from there you can actually know the flow rate of this system. Okay, and you can measure the flow rate lah, basically, of water through the hose or the pipe that you are using. Okay, previously I think I have talked about the pitot probes, also called the pitot tubes, and pitot static probes, named after the French engineer Henri de Pitot. It is a widely used for flow rate measurement. A pitot probe is just a tube with a pressure tab at the stagnation point. Okay, this one. That measures stagnation pressure, while a pitot static probe has both a stagnation pressure tab and several circumferential static. Okay, actually around this, if you look it from the side or from the top, you can see there are some additional small holes on it. Okay, that actually allow the measurement of the static pressure. Okay, and this particular probe is actually divided into two parts. If you can see here, on the outer part, it allows the measurement of the static pressure, and on the center, or the inner part, it allows the measurement of the total pressure. And then both of these part is connected to the pressure meter, so that you can measure the differences, where the differences is your you can calculate the velocity using the Bernoulli equation, etc., etc. Okay. This is the small holes that I talk about. Okay, there are several actually around this tube, or around this probe, that measure the static pressure, and at the front here measure the total pressure. Okay, and the differences between what being measured at from here and here, take the differences, then you get the the dynamic pressure, where from the dynamic pressure you can obtain the velocity of the fluid inside uh, uh, a pipe, a wind tunnel, or you can put this probe on a car, okay, on an aircraft to measure the speed. Okay, anyway, this one, this is an orifice meter and a schematic showing its built-in pressure transducer and digital readout. Okay, where it used the force and magnet, and down here we have a bellow to actually get this reading, okay, to measure the differences of these forces. Then we also have this flow meter to measure the wind speed and temperature. This is more like a more user-friendly mechanism that you can easily measure the wind speed on your own. We do have this mechanism, or we do have this instrument in our lab. So later on, hopefully, when the COVID is ended, you can get a hands-on experience on using this device. Okay, and we do also have ultrasonic flow meters, enable one to measure the flow velocity without even contacting the fluid by simply pressing a transducer on the outer surface of the pipe. Okay, because the pipe will have some sort of changes in the pressure. Okay? And we do also have the hot wire anemometer, which will characterize by its very small sensor at the front here. I'm using this device when I work on my final year project, sometimes in the early 2000. At that time, we developed in-house test section, or not really a test section, but it is rather a complete wind tunnel, open loop wind tunnel, a small size, right? And then we, at the end of that project, we do measure the airflow distribution on inside this the test section of that particular wind tunnel due to the some changes that we did on the inlet of the wind tunnel, or which have a bell curve shape. Okay? And what happened to this hot wire? Actually, the current is applied to this thin wire, and then when the airflow, or the velocity, the airflow, okay, going through this wire, there will be some changes in the temperature, right? So from there, it will actually measure the changes in that, and then transfer it into the the changes in the reading of the electricity, and then convert it into a more readable measure for the velocity or pressure, okay, in the form of that. But there are some what do you call it, pre-measurement, or it's actually, there are one particular term that we use to actually, yeah, calibration. We need to do some calibration before we can actually get or obtain the real data. okay, to make sure that everything is work as it should. And we also have particle image velocimetry, or in short, we call it PIV. It is a well-known device that use the beam of or the sheet form of laser. Okay, then we apply, or we uh, seed, or we actually allow some sort of smoke to cross this beam, the laser beam, and at that laser beam, the camera will be positioned to capture what are the changes on that particular laser beam. Okay, the purpose is actually to see the direction of the particles. Okay, because in that particular smoke, we do release some sort of seeding, okay, a particle, a specialized particle that will be monitored by this video camera. That particular seeding is very, very small, but with the high technology of this video camera, it can capture the motion or the trajectory of that particular particles. And as you can see on this part down here, denoted by this arrow, that is actually where the particle is moving. Okay. And that's all for now. I will go through and I will share you some examples in the next videos. Thank you very much.